Welcome to the deep dive. Today we're plunging into something pretty fundamental, something that literally holds our world together.
Welding.
Exactly, welding. Specifically, we're doing a deep dive into MIG welding. You might know it as Gas Metal Arc Welding, GMAW, especially in the U.S.
Right, and it's everywhere, isn't it? Cars, bridges.
Oh, absolutely. Super versatile, really productive, works on thin sheets, thick plates, most metals, really.
It's one of those things, incredibly common, but the actual process, how it works, not many people really get the physics and the material science behind it.
That's what we're here for. So our mission today, let's unpack the core mechanics of MIG-MAG. We'll look at the big advantages, the practical challenges.
Like maybe demystify some of those key settings welders use to get it just right.
Yeah. The goal is for you, our listener, to walk away with a really solid grasp of this, well, fundamental industrial process. So let's get into the nitty-gritty.
Okay, so at its heart, MIG-MAG involves striking an electric arc. This arc forms between a wire electrode that's fed continuously and the metal you're welding, the workpiece.
And this arc is hot enough to melt both.
Exactly. It melts the wire and the base metal. They mix together in this molten weld pool, and then it solidifies, creating the joint.
So the wire is doing double duty.
Precisely. It's not just filler metal being added. It's actually the source of the heat through the arc at its tip, and it becomes the filler metal. It's kind of like a two-in-one deal.
Okay, so this wire is like the star player. How does it get where it needs to go? What else is happening right there at the weld?
Good question. The wire comes off a reel driven by a motor. It passes through this copper contact tube.
Copper for conductivity.
Right. That tube feeds the welding current directly into the wire just before it hits the arc. Then around that, there's a nozzle.
And that's for the gas.
Yes, the shielding gas. It flows out and blankets the molten weld pool, protecting it from the air.
Protecting it from oxygen and nitrogen, things like that.
Exactly. Without that gas shield, the atmosphere would react with the molten metal. You'd get contamination, porosity, basically a really poor, weak weld.
Makes perfect sense.
Yeah.
Okay, we've got the arc, the wire, the gas. What about the overall setup? Like, how automated is this? Is it always a person holding the torch?
Good point. There are different levels. Mostly you see three main types. First is semi-automatic. This is probably the most common.
Okay.
Here, the machine controls the wire feed speed and keeps the arc length pretty steady automatically. But the welder, they're manually controlling the travel speed, how fast they move along the joint, and exactly where the wire is pointed.
My hands-on part.
Then you've got mechanized welding. Here, pretty much all the parameters are automatically controlled, speed, position, everything. But an operator might still be there to, say, steer the welding head slightly or tweak the settings during the weld.
So more automated, but still needs oversight.
Yeah. And finally, there's fully automatic. Once it's set up and started, there's no manual intervention needed during the welding process itself. Think robots on an assembly line.
Okay, got it. So we know what it is, how it basically works. Why choose MIG-MAG? What are its superpowers? Why is it so popular?
Productivity, that's the big one, because that wire feeds continuously. You're not stopping to change electrodes like in, say, stick welding or MMA.
Oh, no stub ends.
Exactly. So you get a really high deposition rate. That's how much welded metal you put down per hour and very few stops and starts. That makes it incredibly economical. It's a real powerhouse for just getting metal joined quickly.
And you mentioned that automatic arc length control. That sounds like it helps keep things consistent.
It absolutely does. It's a smart process in that way. Plus, it's generally considered a low hydrogen potential process.
Low hydrogen. Why is that important? What does hydrogen do to a weld?
Hydrogen is a welder's enemy. Even tiny amounts can get trapped in the weld metal as it cools, and it can lead to microscopic cracks, sometimes delayed cracks that appear hours or days later. Seriously.
Oh, yeah. It's called hydrogen-induced cracking, or cold cracking. It severely weakens the joint. So a process that inherently introduces less hydrogen is a big plus for weld integrity, especially in critical applications.
Okay, wow. So productivity, consistency, low hydrogen risk. What else? Any practical benefits for the welder?
Definitely. You generally have good visibility of the weld pool and the joint line, which helps with control. And usually there's very little slag to clean off afterwards, unlike stick welding. That saves a lot of time.
No chipping hammers needed then.
Not usually, no. It can also be used in all positions, flat, horizontal, vertical, overhead, especially with certain techniques we'll probably get into, like dip transfer.
Okay.
So yeah, overall, good process control possibilities, a huge range of applications. Sounds almost perfect. But, every superhero has its kryptonite. Where does MIG-MAG stumble? What are the challenges, the tricky bits?
Well, for one, while it's automated in some ways, you don't have independent control over the filler addition rate separate from the heat input. They're linked through that wire feed speed and current relationship.
Ah, so you can't just add more metal without also adding more heat, generally speaking.
Right. Which can be a limitation for certain specific, very precise jobs. Also, finding the sweet spot, the optimum parameters to minimize spatter, that can be tricky.
Spatter those little balls of molten metal that fly off.
That's the stuff. It doesn't usually harm the weld strength itself, but it looks messy and needs to be cleaned off, which adds cost and time. Excessive spatter can sometimes indicate an unstable arc, though, which might point to other issues.
Yeah, okay, so mainly a cleanup hassle, but maybe a warning sign sometimes? Are there more serious risks, like defects in the weld?
Yes, there's a definite risk of lack of fusion. This is where the weld metal doesn't properly fuse to the base metal or the previous weld run. It's a particular concern with the dip transfer mode, especially on thicker materials.
Like leaving a gap hidden inside the weld.
Exactly. A potentially dangerous defect. Also, some MIG-MAG methods, particularly spray transfer, run at higher heat inputs. This can sometimes lead to high hardness values in the heat-affected zone, the area right next to the weld.
High hardness. I thought harder was stronger. Why is that a problem?
That's a common thought, but excessive hardness often means increased brittleness. A very hard, brittle zone is more likely to crack under stress or impact. You generally want a good balance of strength and toughness or ductility.
Right, you don't want it to shatter. What about the gear itself, or where you're welding?
The equipment is generally more complex and expensive than, say, a basic MMA or stick welding setup, and it needs more maintenance, wire feeders, liners, contact tips, gas systems.
Lots of moving parts.
Yeah, and a really critical one for site work. The gas shield is easily blown away by drafts or wind.
So welding outside on a windy day is a problem.
A big problem. You need screens or some kind of shelter to protect that gas shield. If it gets disrupted, you'll get porosity and contamination, guaranteed.
Okay, any other limitations?
Well, the torch can be a bit bulkier than an MMA electrode holder or a TIG porch, so getting into tight joints can sometimes be harder. And it doesn't handle dirty or rusty base metal as well as stick welding, which has flux to help clean things up. MIG-MAG prefers clean material.
Gotcha. Cleanliness is key. So, okay, it's powerful but needs care. Let's talk controls. What's on the welder's dashboard, so to speak? What are they adjusting?
Right, this is where the skill comes in. The primary variables are welding current, which is directly tied to wire feed speed.
Well, you adjust one, the other follows.
Pretty much, yeah.
Hmm.
Then there's voltage. The type of shielding gas is crucial. Travel speed, how fast you move the torch, electrode orientation or torch angle. Inductance, which is mainly for dip transfer. Then there's the contact tip to work distance CTWD.
Okay.
And finally, the nozzle to work distance, which affects the gas coverage. They all interact, so it's a balancing act.
Whoa, that's a list. If you had to pick, like, the top two that a beginner needs to grapple with first, what would they be? The ones with the biggest impact.
Definitely voltage and wire feed speed. Those set your basic power level and how much metal you're depositing. Get those roughly right for your material and thickness, and then you fine-tune with the others.
Okay, voltage and wire feed speed. You said wire feed speed controls current. What kind of weight were you talking about, size-wise?
Generally, common diameters range from about 0.6 millimeters, so quite thin, up to maybe 1.6 millimeters. Sometimes larger for specialized applications, but that's the typical range.
And voltage, you said it's maybe the most important. What does it primarily control?
Voltage is the main handle for controlling arc length, especially in spray transfer. Think of it like the gap the arc has to jump. In dip transfer, it's a bit more complex. It affects how quickly the current rises during the short circuit and the overall heat input.
And little things matter here, right? Like connections.
Hugely important. Poor electrical connections, a loose ground clamp, a worn cable, they cause voltage drops. And even a small drop can really mess with the arc stability and performance. It's something experienced welders check constantly.
So if your voltage is set too high, or effectively too high because of drops elsewhere, what bad things happen to the weld?
Too much voltage can cause problems like porosity, little gas bubbles trapped in the weld, excessive spatter, and undercut. Undercut is where the arc gouges into the base metal along the edge of the weld, leaving a notch. All bad for quality.
Right. Okay, let's talk about that unsung hero,
Oh,
the shielding gas. This is where MIG versus MAG comes in, isn't it?
exactly. This is a really key distinction. It all depends on the gas. If you're welding non-ferrous metals, think aluminum, copper, nickel alloys, you have to use an inert gas.
Inert meaning it doesn't react.
Correct. Pure argon or maybe argon mixed with helium. These gases don't react with the molten weld pool. That's critical because those metals are very sensitive to oxidation. This is MIG metal inert gas.
Okay, MIG, non-ferrous plus inert gas. What about steel?
For steels, including stainless steels, you use active gases. This means you start with argon, but you deliberately add a small, controlled amount of an active gas, like carbon dioxide, CO2, or sometimes oxygen.
Active meaning it does react.
Yes, in a beneficial way. These small additions react with the molten steel to help stabilize the arc and improve how the molten droplets wet or spread out on the base metal. This is metal active gas.
Ah, okay. So the gas choice fundamentally changes the name and the application. That clarifies a lot.
It really does.
Yeah.
Same basic equipment, different gas, different name, different materials.
So what are the common gases or mixes then? You mentioned pure argon for aluminum.
Right. Pure argon works well for aluminum, partly because aluminum naturally forms a surface oxide layer that helps stabilize the arc. It can be a bit tricky for really reactive metals like titanium, though. And remember, argon is heavier than air.
You mentioned that about 1.4 times denser.
Yeah, which is great for shielding in the flat or downhand position. It forms a nice blanket. But it also means in confined spaces, it can displace air and become an asphyxiation hazard. Ventilation is super important.
Good safety point. What about adding helium to the argon? Why do that?
Helium makes the arc hotter. It has higher thermal conductivity. So argon-helium mixes are good for thicker materials or metals that conduct heat away really quickly, like copper and thick aluminum.
Gives it more punch.
Sort of, yeah.
Mhm.
More helium generally means deeper, broader penetration. The downside can be a slightly less stable arc and potentially more spatter than pure argon. It's very effective, though, at preventing lack of fusion on thick aluminum sections.
Okay, now CO2. I hear about
Yeah.
that a lot for steel welding, sometimes just pure CO2.
Yes, 100% CO2 is used. It's cheap, and it gives very good, deep penetration, which is great for thicker carbon steels. However,
There's always a however.
right, pure CO2 promotes what's called globular transfer. Instead of a nice spray of droplets, you get these big, irregular blobs of metal transferring across the arc. It's quite an unstable, violent arc, produces a lot of spatter.
Doesn't sound ideal.
It's not for everything. And importantly, you cannot achieve a smooth spray transfer with pure CO2. So it's mainly used for carbon steels, some low alloy steels, often in mechanized setups where spatter is less of a concern.
So how do you get the best of both? Good penetration, but less spatter. Mix them.
Exactly. Argon CO2 mixtures are probably the most common for mag welding steels. Adding just 5 to maybe 20% CO2 to argon gives them a good balance. You get better penetration than pure argon, but a much more stable arc and way less spatter than pure CO2.
The sweet spot.
Pretty much. The argon stabilizes the arc, the CO2 gives it that penetration boost and helps with the wetting. For stainless steels, you use even less CO2, maybe 1 to 5%, or sometimes a tiny bit of oxygen instead.
Why less for stainless?
Stainless steel relies on chromium for its corrosion resistance. Too much CO2 or oxygen in the shielding gas can oxidize that chromium in the weld, reducing its effectiveness. So you keep the oxidizing potential really low, like max 2 or 2.5% CO2, to maintain that corrosion performance.
Makes sense. You also mentioned adding helium sometimes for stainless.
Yeah, especially for austenitic stainless steels, which have low thermal conductivity. Adding helium, sometimes quite a lot, up to 85%, helps get a hotter arc and better heat spread to avoid lack of fusion defects, similar to its use in aluminum.
Fascinating how critical the gas choice is. Okay, moving on. How does the welder's technique, their movement, play into this? Travel speed, torch angle.
Oh, hugely important. Travel speed is a big one. If you travel too fast, you don't put down enough metal, the bead gets narrow and ropey, penetration decreases, and you risk undercut along the edges.
And too slow.
Too slow, you put in too much heat, the weld bead gets excessively wide, could lead to burn through on thinner material, or just waste time and consumables. Torch angle also matters a lot, whether you're pushing the puddle or dragging it, and the side angle affects penetration shape, and again, the risk of undercut. It's all part of the welder's craft.
So many things to balance.
Yeah.
Let's talk about CTWD, contact tip to work distance. Sounds technical, but you hinted it does something interesting with the current.
It does, yeah. CTWD is simply the distance from the very end of that copper contact tip inside the nozzle to the surface of the workpiece. What's critical is the length of wire sticking out beyond the contact tip. We call that the electrode extension or stick out. That length of wire has electrical resistance. As the welding current flows through it, it heats up due to resistance like the element in a toaster, just less extreme. This preheats the wire before it even reaches the arc.
Ah, so the longer the stick out, the more preheating.
Exactly. And because the wire is already partly heated, the arc doesn't need quite as much current to melt it off at the same wire feed speed.
Wait, so increasing the CTWD, increasing the stick out, actually reduces the current for a given wire feed speed.
Correct. It's a bit counterintuitive, but yeah, longer stick out equals lower current.
So how do welders use that? You mentioned maybe increasing deposition rates.
Right. In mechanized or robotic welding, they might deliberately use a longer CTWD. This allows them to increase the wire feed speed, pushing more wire through while keeping the actual welding current at a manageable level. The resistive heating helps melt that extra wire, so you effectively get more metal deposited per minute.
That's a clever trick for automation. What about manual welding? What happens if your CTWD is way off? Too long or too short?
If it's too long, say you're holding the torch too far away, the current drops, and you might get lack of penetration, especially down in a deep groove. If it's too short, you risk overheating the contact tip in the nozzle, maybe even melting the tip. Plus, it can make the arc harsher.
So there's a recommended range.
Definitely. It depends on the transfer mode. For dip transfer, it's usually shorter, maybe 10 to 15 millimeters. For spray transfer, a bit longer, perhaps 20 to 25 millimeters. And for pulsed, somewhere in between 15 to 20 millimeters, roughly.
And nozzle distance, is that different from CTWD?
Slightly. The nozzle is the outer part that directs the gas. Nozzle to work distance mainly affects how wide the shielding gas covers the weld pool. Too far away, and the gas shield gets blown away easily. Typical distance is around 12 to 15 millimeters.
Okay, got it. So settings, gas, movement. Now, the really cool part, how the metal actually jumps from the wire to the workpiece.
Yep.
This arc dance you mentioned, the different transfer modes.
Yeah, this is where the physics gets really interesting, and it changes dramatically depending on your settings. Let's start with dip transfer.
Dip transfer. Sounds like it takes a dip.
Literally, the wire flats down and actually touches or dips into the molten weld pool. This causes a short circuit. The current surges, the end of the wire heats up explosively, detaches, and creates the arc again. Then the wire feeds down and dips again.
Wow, how often does that happen?
Fast. Anywhere from, say, 50 to 200 times per second. It's a very rapid short-circuiting cycle.
That sounds aggressive. What's it good for?
Because it's constantly shorting out, the average heat input is relatively low. That makes it great for welding thin sheet metal, maybe 0.8 up to about 3.2 millimeters thick without burning through. It's also excellent for welding in positions other than flat vertical up overhead because the weld pool is small and freezes quickly. And it's often used for root runs in pipe or plate welding.
Any downsides?
Well, because it's inherently a short-circuiting process, it can be prone to spatter if the settings aren't perfectly tuned. And there's that risk of lack of fusion, especially if the heat input is too low for the material thickness. Also, it's generally not used for non-ferrous metals like aluminum. They don't like that short-circuiting action.
Okay, low heat, thin stuff, positional. What's next? Spray transfer.
Right. Spray transfer is quite different. Here you're using higher currents and voltages. The tip of the wire melts, and tiny droplets detach and are propelled or sprayed across the arc gap to the workpiece. There's no short-circuiting.
Like a fine mist of metal.
Exactly. It's a very smooth, stable arc with very little spatter. Because you're using higher energy, you get high heat input and high deposition rates.
It sounds great. Where do you spray?
It's mainly used for thicker materials.
Yeah.
Steel's generally over 6 millimeters thick. Aluminum alloys over 3 millimeters. It produces really nice, smooth welds.
Limitations.
The main one is position. Because of the high heat and the very fluid weld pool, spray transfer is mostly limited to welding in the flat position, what we call downhand butt welds or maybe horizontal vertical fillet welds. Try to use it vertically or overhead, and all that molten metal would just drip out.
Gravity wins. Okay, so dip for thin positional, spray for a thick flat. What bridges the gap? You mentioned pulse transfer.
Pulse transfer is the clever one. Think of it as a modified spray transfer. It uses pulses of high current superimposed on a lower background current. During the high pulse, one or more droplets detach and spray across the arc, just like in spray transfer. But then the current drops low enough to keep the arc alive without transferring metal, allowing the puddle to cool slightly.
So it pulses between high energy transfer and low energy weighting.
Basically, yes. This allows you to get that nice, spatter-free, free-flight droplet transfer, like spray, but at a much lower average current and heat input.
What are the benefits of that?
Huge benefits. You get very low spatter across a wide range of settings. The heat input is lower than conventional spray, which reduces distortion and is better for some materials. Compared to dip transfer, you get much less risk of lack of fusion. And crucially, it allows you to achieve that spray-like transfer in all positions, even on thinner materials sometimes. You can also use larger diameter wires on thinner plate, which can be cheaper and easier to feed.
So it kind of gives you the best of both worlds.
In many ways, yes. It extends the advantages of spray transfer down to lower currents and into positional welding. This is where those synergic machines really shine.
Ah, synergic. You mentioned that. I always pictured something from Star Trek. What does it actually mean for the welder using it? How does it simplify things compared to, say, setting up pulse manually?
Yeah, it sounds futuristic, but it's actually brilliant engineering. Before synergic sets, setting up pulsed welding was a nightmare. You had to manually adjust the peak current, the background current, the pulse time, the background time, all these variables, trying to find the right combination for your wire, gas, and material. It took ages and lots of expertise.
Sounds complicated.
It was. Synergic systems changed that. Manufacturers did all that hard work. They pre-programmed the relationships between all those pulse parameters for specific combinations, like, say, 1.2 millimeter stainless steel wire with an argon 2% CO2 gas mix.
So the machine knows the recipe.
Exactly. The welder selects the program for their material, wire, and gas. Then often there's just one knob. As you turn that knob, usually adjusting the wire feed speed, the machine automatically adjusts the voltage and all the complex pulse parameters in Synergy to maintain a stable, optimized arc for that addition.
Wow, so one knob does all the heavy lifting based on the program.
Pretty much. It makes setting up for high-quality pulsed welding vastly simpler and faster, ensuring you get a balanced arc condition without needing a PhD in pulse physics. It really democratized the use of advanced pulse techniques.
That's a huge leap. Okay, any other transfer modes? You mentioned globular earlier, associated with CO2.
Yes, globular transfer. This one is sort of the awkward middle ground between dip and spray, often occurring with pure CO2 or sometimes argon-rich gases at settings too high for dip, but not high enough for a true spray.
And it's...
Blobby.
That's a good word for it. Large, irregular molten droplets form on the end of the wire, kind of wander around in the arc, and then detach mainly due to gravity. It's inherently unstable, produces a lot of spatter.
That sounds very useful.
It's not widely used, especially manually. You might see it in some mechanized applications on medium thickness steel, maybe 3 to 6 millimeter welded flat. But it often comes with risks like lack of penetration, fusion defects, and just generally uneven, poor-looking welds. It's usually a mode you try to avoid or transition through quickly. Right. Aim for dip, spray, or pulse. Okay, one more variable you mentioned specifically for dip transfer, inductance. What's that doing?
Inductance. It's like the unsung hero of dip transfer. Remember how dip transfer involves rapid short circuiting?
Yeah, 50 to 200 times a second.
Okay, now imagine what happens electrically during that short circuit. The resistance drops to almost zero. Without inductance, the current would try to surge to an incredibly high level almost instantly.
Like a dead short. Zap.
Exactly. It would be like a tiny explosion at the wire tip every single time it touched the pool. Massive spatter, unstable arc, just uncontrollable.
So inductance prevents that explosion. How can you give us an analogy?
Think of inductance in an electrical circuit, like a flywheel or maybe a shock absorber in a mechanical system. It resists rapid changes in current flow. So when that short circuit occurs, the inductance slows down the rate at which the current can rise.
It smooths out the surge.
Precisely. It slows the current rise enough to allow the wire tip to heat up and detach more controllably, pinching off the droplet without that violent explosion. It makes the dip transfer process much smoother and reduces spatter.
Is there an ideal setting?
Yes, there's an optimum level. Too little inductance, and you still get that explosive spatter. Too much inductance, and the current rises too slowly, the arc might extinguish, or the wire might just stub into the base metal without melting off properly. Thankfully, many modern power sources have presets or automatically adjust the inductance for optimal performance based on other settings.
Clever machines. Okay, so if someone wants to get started, what's the essential kit they need? The welder's arsenal for MIG-MAG.
All right, the core components. You need a power source, usually a constant voltage CV type. Could be an older transformer rectifier or a modern inverter. Then the torch assembly, that's the gun itself, with its trigger, cable, and the crucial parts inside. The liner the wire runs through, the contact tip, the gas diffuser, and the outer nozzle.
Got it. Power source torch.
You need a wire feed unit. Sometimes this is built into the power source, sometimes it's a separate box. This has the motor and drive rolls that push the wire. Power and return cables, obviously. The gas cylinder with the correct shielding gas, plus a regulator and flow meter to control the gas flow, and of course, a spool of the correct electrode wire.
Seems like a fair bit of kit. Now, assuming you have all that, quality control sounds huge. What are the absolute must-do inspection points before you even strike an arc and during welding?
Absolutely crucial. Prevention is way better than cure here. First, just a general visual check is the equipment in good condition. Cables not frayed, connections tight.
Basic safety and function.
Right. Then, the wire itself. Is it the correct diameter for the job and for the contact tip and drive rolls? Is it the right specification for the metal you're welding? What's the quality like? Look at the deoxidation levels. More deoxidizers in the wire help prevent porosity. And even how it's wound on the spool matters.
Wound on the spool. How does that affect things? Are there specific wire quality things that cause the most common headaches if you ignore them?
Oh, definitely. A poorly wound spool random winding versus layer or precision layer winding can cause the wire to snag or tangle during feeding. That leads to an erratic arc, inconsistent welds, major frustration. Also, that deoxidant level is key. If you use a wire with insufficient deoxidants for the job, especially if the base metal isn't perfectly clean, you're asking for porosity. It just can't scavenge those impurities effectively. And check for things like copper coating on steel wires that helps with current transfer and prevents rust, but make sure it's consistent.
Good tips. Okay, wire checked. What's next on the list?
Drive rolls in the feeder, are they the right size and type for the wire? Smooth groove for solid wires, V groove or knurled for flux cord sometimes, U groove for soft wires like aluminum. Is the pressure set correctly? Too loose, it slips. Too tight, it can deform the wire and cause feeding problems.
Right. The feed needs to be smooth.
Critical. Then the liner inside the torch cable again, correct size, clean, not kinked. Steel liner for steel wires, Teflon or nylon for aluminum. The contact tip, this is a high wear item. Check it's the right size for the wire, check the hole isn't worn oval, replace them regularly.
Because that's where the current transfers right at the end.
Exactly. A worn tip means poor current transfer, unstable arc. Then check all your electrical connections are tight torch connection, ground clamp. Loose connections mean voltage drops and arc problems.
We talked about that.
Gas. Check you have the right gas type connected, plenty of gas in the cylinder, and set the correct flow rate at the regulator flow meter. Enough flow for good coverage, but not so much becomes turbulent and pulls in air.
And then double check your main settings.
Always. Wire feed speed, voltage, travel speed, check them against the approved welding procedure specification, WPS if you have one. And don't forget safety checks. Equipment duty cycle, electrical insulation good, fume extraction working properly. Is the welder actually qualified for the procedure they're about to perform?
Lots to keep an eye on. So things do go wrong, despite the checks. What are some typical flaws or imperfections you might see in a MIG-MAG weld?
Common ones include silica inclusions, especially on ferritic steels, that's your basic carbon and low alloy steels. They look like little glassy islands trapped in the weld, often from not cleaning properly between weld passes.
So, cleanliness again.
Always. Lack of sidewall fusion is another, particularly with dip transfer when welding thicker material vertically down. The weld metal just doesn't bite into the side of the joint. Porosity, those gas bubbles, usually caused by losing the gas shield or welding on contaminated material, oil, grease, paint.
Right.
And burn through, especially on thin sheet metal if you use the wrong mode, like try and use spray transfer or just having your settings way too high. I remember seeing a beginner once tried welding some thin gauge sheet with full spray transfer.
Uh-oh.
Yeah, it looked less like a weld and more like a piece of metal lace afterwards. Holes everywhere, classic burn through. Taught him pretty quickly why choosing the right transfer mode for the thickness is vital.
A memorable lesson, I bet. Okay, we focus heavily on MIG-MAG with the external gas shield. But you mentioned a cousin process earlier, flux cord arc welding, FCAW. How does that fit in?
FCAW is a really significant development, especially for semi-automatic welding out on site. It became popular around the mid-1980s. The key difference is the wire itself. It's tubular, not solid.
Cord, like it has something inside.
Exactly. Inside the hollow wire is a granular flux. This flux does similar things to the coating on a stick. Electrode provides shielding, adds deoxidizers, maybe stabilizes the arc.
So the shielding comes from inside the wire.
It can, yes. Some types of flux cord wires contain gas-producing elements within the flux. When the arc heats it, this flux generates its own shielding gas cloud around the arc. These are called self-shielded FCAW wires.
Ah, so no separate gas cylinder needed.
Correct. That's the huge advantage for site work. No gas bottle to lug around and much less sensitive to drafts blowing the shield away. Makes semi-automatic welding practical in conditions where traditional MIG-MAG would really struggle.
That's a game changer for outdoor work. Are there other types of flux cord wire?
Oh, yes. Besides self-shielded, there are gas-shielded FCIW wires, which do still require an external shielding gas, often CO2 or an argon mix, just like mag welding. These often give better performance or properties. You also get different flux types within those categories. Rutile types are good all-round, easy to use positionally. Basic fluxes handle dirtier material better and give tougher welds. And there are metal cord wires too, which are like a metal powder inside instead of flux, giving very high deposition rates, almost like spray transfer, but sometimes easier to handle.
Lots of options there too. One quick note on cord wires: if they get damp, can you just bake them like stick electrodes?
Generally, no. Baking flux cord wires if they've picked up moisture is usually ineffective and not recommended by manufacturers. Unlike solid wires, once moisture gets into that core, it's pretty much impossible to drive it out reliably without damaging the flux. Best practice is good storage to prevent moisture pickup in the first place.
Good to know. Okay, we've covered a huge amount of ground. Let's try to bring it all together for you, our listener. MIG-MAG in a nutshell. What are its core strengths, the reasons it's so widely used?
Okay, summary. High productivity is number one, thanks to that continuous wire feed. Ease of automation, from simple mechanization to full robotics. All position capability, especially using dip or pulse transfer or switching to FCAW, it can handle a really wide range of material thicknesses, from thin sheet to heavy plate. And yeah, that continuous electrode means fewer stops and starts, higher efficiency.
And the flip side, the main weaknesses or challenges to keep in mind.
The potential for lack of fusion defects, particularly with dip transfer if not applied correctly. The range of available consumables isn't quite as vast as for, say, MMA welding. The definite need for site protection against drafts if using gas-shielded versions. The equipment is more complex and costly than basic stick welding. And a big one, especially with spray and pulse modes, it produces higher levels of ozone gas than many other processes, so good fume extraction is absolutely critical for welder safety.
Right, safety first. Okay, that's a great overview.
Yeah.
So, thinking about everything we've discussed, this intricate dance of variables, the physics of the arc, the need for precise control, it leads to a final thought. Given how complex MIG-MAG welding is, but also how automated it can be, where do you think advancements in things like AI and robotics might push the boundaries next? Could we see systems that adapt settings in real time with even greater precision, maybe making it even more accessible or tackling applications we haven't even thought of yet? What might that unlock? Something for you to ponder after our deep dive today.